So we want to optimize electrode skin interface. So, but what is really at the skin, electrode skin interface? So our skin consists of epidermis, dermis, and hypodermis. So the outermost layer of the epidermis is called stratum corneum. This is a electrical insulating layer. It consists of essentially dead cells. So it's about 10 to 100 micrometers thick and it's insulating. So that creates a lot of impedance on the skin. So the underlying, dermis and hypodermis are much more conductive. So we can consider them, purely resistive. So if you build an electrical model for the electrical skin interface, you have, the purely resistive dermis and hypodermis. You have your epidermis, which is very insulating. So that can be, modeled as an RC, which in parallel, RC captures the conductive, properties, and C captures the, capacitive property of, the interface. Then you also have your electrode. So in this system, the dominating impedance is here at the epidermis layer. So that's why in clinical standards, we use white electrodes. We use, gel electrodes. If you have ever done ECG, or seen people doing ECG, you probably have seen this kind of gel electrodes. So this kind of gel electrodes can hydrate the skin to reduce resistance. They also are typically relatively soft, so they can form a conformal contact with the skin without any air gaps. But they can just they dry up really quick in 24 hours, so they are not suitable for wearable applications. They are really just for spot checking. So to continuously monitor ECG in wearable applications, we use dry electrodes. So electrodes without, gels. And on the right, I'm showing a skin replica. So this is skin. This is skin. And you see it's not very smooth, it's wrinkled. Then the yellow thing here is the ECG electrode. So I put a picture right here. So can you tell me why is a good electrode for ECG? Why does it satisfy the requirements of ECG electrodes? So first, flexible. Is it flexible?
Yeah.
Why is it flexible?
Super thin ribbon.
Super thin ribbon. Okay. Is it stretchable?
Yeah.
Because you have this
wavy pattern.
Yeah, wavy pattern. And is it water permeable?
It's so thin.
How do we make it water permeable?
Make a lot of holes. Yeah.
A lot of holes. Yeah, this is a like open mesh structure, so water can come out. And this is made of gold, so that's why it has low impedance. So this is a kind of drug electrodes we use in wearable research, and it's often called ETA2. So this is a system made of ETA2, very similar structure, and it's flexible because we are using very thin gold chassis. It's stretchable because we are using serpentine chassis, and it's water permeable because it has an open mesh design. And you can see you can capture pretty good, but not ideal. ECG, you don't see the P and T here. There's still improvement we can do. So how can we fabricate ETA2? So this is typically done by microfabrication. You first microfabricate this pattern on a silicon wafer. Then you use a stamp to pick this structure up. Use a stamp to pick the structure up from the silicon wafer. Then on your skin, you are going to spray a glue layer, which is conductive. Then you put a stamp on the glue. Then you remove the stamp. Then the ETA2 will stay on skin. So that's how we, fabricate ETA2s. So ETA2s can, collect a very high quality ECG compared to standard gel electrodes. So the problem with gel electrodes, first they dry up very easily. Second, they're relatively bulky. That means since they are relatively bulky, that means they are not very they are unable to stretch with the skin. So when you move your hand, when you like move your fingers, there will be relative displacement between your gel electrodes and the skin. That creates motion artifacts. You won't get a very clean signal when you use gel electrodes. But with e-tattoos, you can see, you can get a very consistent ECG signal, even you are, doing different, gestures, So that's, so that's one advantage. E-tattoos resist motion artifacts. And they can also support long-term monitoring. So this is another e-tattoo, but we pattern the e-tattoo on the ear near the brain. So this can be used to record EEG, another type of electrophysiology. You will see, when you open or close eyes, you see different EEG pattern, and this supports long-term, like 2 weeks recording continuously. So this is because this open mesh design prevents moisture buildup, so they can stick to the skin, even when you sweat. This is a more advanced system of e-tattoo, and we even integrated semiconductor chips on the device. So you have these zigzag traces that serve as like copper wire, so they connect all the chips on this system, and under the circuit, there's even a microfluidic chamber. It's like a cushion. It's like a buffer, so that the baby when wearing the device, the baby will feel more comfortable because there's a fluid layer, fluid cushion that serve as that decouples the very hard chips from your skin. So using this system, you can still, monitor, ECG and even PPG. You can use e-tattoo to build circuits. So contact, type of, dry electrodes. There's also capacitive dry electrodes. This is essentially electrode. This is essentially, an electrode with an insulator. So you put an insulator on the skin. So the reason here is that, sometimes those dry electrodes or gel electrodes can cause some irritation. That's one of the drawbacks, but this is not a major drawback. But this type of capacitive electrode is highly sensitive to motion artifacts. So let's say we have a ECG signal in the skin, then this voltage is going to charge this capacitor, right? This is a capacitor, electrode, insulator, and also this is something conductive. So this is a parallel plate capacitor. Then it can couple ECG signal capacitively. The problem with this type of non-contact or capacitive sensor electrode is that they are highly sensitive to motion artifacts. So when there's someone moving around, so let's say you have the capacitive electrode and I walk by, then that's going to create noise because because everything is coupled capacitively. So to solve this issue, they typically have some kind of shielding, outside your sensing electrode. So this is like a Faraday cage, if you are familiar with that. They have to build a Faraday cage to shield the sensing electrode. So this can be, make your system relatively bulky. So because of these reasons, capacitive electrodes are not very widely used in wearables. Go ahead.
Would there also be noise just from the top plate moving up and down a little bit?
Yeah. So top plate